Bismillahirrahmanirrahim. In today's lecture, we will be covering rest of the portion of chapter 7, combustion. So, in previous lecture, we have studied about the combustion in an SI engine, how it happens, the three broader region or phases of the combustion. First is the flame ignition and development, then flame propagation, and then the last one is flame termination. Okay. Now, what is happening inside the combustion chamber what is the effects of this combustion on engine operating characteristics? Let's see. First, in power operation, for maximum power at wide open throttle, fuel injectors and carburetors are adjusted to give a rich mixture, and ignition systems are set with retarded spark plugs. When we have a wide open throttle condition, so it means more amount of air. When more amount of air is going in or flowing inside the combustion chamber, so we require maximum amount of fuel to have that stoichiometric ratio, so that fuel injectors and carburetors are adjusted to give that types of a mixture. So an ignition system in these conditions are set with retarded spark plugs. Another way of obtaining added power from an engine is to operate with a lean mixture, normally used in sports car. In lean mixture, flame speed is slow and combustion lasts well past TDC. So this is the characteristic of a combustion when we have a lean mixture. The flame speed is slow and the combustion lasts well past TDC. Now in cruising operation, what are the engine operating characteristics with respect to the combustion? For cruising operation, less power is needed and brake specific fuel consumption becomes important. So for in cruise speed or cruise operation, the brake specific fuel consumption is important and the power is of less important. A lean mixture is applied to the engine. High EGR, exhaust gas residue, is used and ignition timing is advanced to compensate for the resulting slower flame speed. So a lean mixture is applied to the engine, high exhaust gas residue is used, and in ignition timing is advanced. Here in power operation, when we avoid open throttle condition, the ignition system are set with retarded spark plug, but here we are advancing the ignition timing to compensate the resulting slower flame speed. Fuel usage efficiency, miles per liter, will be high and thermal efficiency will be low. This is because the engine will be operating at a lower speed, which gives more time per cycle for heat losses from the combustion chamber. So maximum time will be available for that heat losses from the combustion chamber. Now, when we have the idle or low engine speed, what are the engine operating characteristics with respect to the combustion? At very low engine speeds, the throttle will be almost closed, resulting in a high vacuum in the intake manifold. So when we have a wide open throttle, it means maximum amount of air is going in. Now we have idle or low engine speed, means at almost the throttle valve is closed. When we are having this condition, it will create high vacuum in the intake manifold. This high vacuum and low engine speed generates a large exhaust residue during valve overlap. So this high vacuum and intake in the intake manifold will and low engine speed generates large exhaust residue during valve overlap. This creates poor combustion. So due to this, we have a poor combustion, which is avoided by supplying a rich mixture to the engine. The rich mixture and poor combustion contributes to high exhaust emissions of hydrocarbon and carbon monoxide. Misfires and cycles where only partial combustion occurs in some cylinders are more common at idle speed. So misfiring of the engine is normally common at idle speed. A 2% of misfire rate would cause exhaust emission to exceed acceptable standard by 10 to 200%. So only 2% of misfire rate would cause exhaust emission to exceed acceptable standards of by 100 to 200%. Now, the last condition, when the closing throttle at high engine speed, when this will happen, when quickly deceleration is desired and the throttle is closed at high engine speed, a very large vacuum is created in the intake manifold. Let's suppose we are going at a very high speed, more than 100 kilometers per hour, and suddenly you pull the accelerator pedal, or you applied less pressure on the accelerator pedal, so the throttle valve is closed, and but the speed is very high. It will create a very large vacuum in the intake manifold system. High engine speed wants to a large inflow of air, but the closed throttle allows a very little air flow. So there is a restriction in the airflow. The result is a high intake vacuum, high exhaust residue, a rich mixture, and poor combustion. Misfire and high exhaust emissions are very common with this kind of operation. Now, the last condition, the starting a cold engine. When a cold engine is started, an over-rich supply of fuel must be supplied to assure enough fuel vapor to create a combustible gas mixture. So when we have a cold starting, or engine is very cold in winter conditions, an over-rich supply of fuel must be supplied to assure enough fuel vapors to create a combustible gas mixture. When the walls of the intake system and cylinders are cold, means all the body of the engine block and heads are in cold winter, a much smaller percentage of the fuel will vaporize than in normal steady state operation. The fuel is also cold and does not flow as readily. So everything is cold, so it will be restriction to the flow. The engine turns very slowly in the cold starting, being driven only by the starting motor, and a greater amount of the compressive heating during compression is lost by heat transfer to the cold valve. So almost 70 to 80% of your compressive heating, and sometimes even more, is during compression is lost to the heat transfer to the cold valves. This is made worse by the cold viscous lubricating oil. So after the body is cold, the fuel is cold, the oil is also cold, and the water inside the cooling chamber is also cold. So everything is cold. So this made worse by cold viscous lubricating oil that resists motion and slows the starting speed even more. All of these factors contributes to a need for a very rich air-fuel ratio when starting cold engine. An air-fuel ratio as rich as 1:1 are sometimes used. So instead of 15:1, we have a air-fuel ratio 1:1. Special starting fluids can be purchased for adding engine startup in extremely cold temperature. So some additives are used with your fuel for easy starting in the cold extreme conditions. Now, the modern fast burn combustion chamber, as we have studied in chapter 6, same figure here with most in figure A, more of the clearance volume on the center line and mostly in the engine head. The clearance volume is mostly in the engine head at on the center line of the cylinder. And in second condition, the clearance volume, the clearance space, more of the space available on the piston head here, bowl. Combustion chamber geometry of modern automobile engines with most of the clearance volume near the center line of the cylinder. This is the center line of the cylinder. So most of the clearance volume is around this center line. This increases squish and tumble and decreases the flame travel distance for most of the combustion process. It will increase the squish and tumble moment and decrease the flame travel distance for most of the combustion process. Engine can be built with the clearance volume in the cylinder head the clearance volume in the cylinder head, this one, or as a bowl in the crown of the piston face, or as a combination of these. The bowl as a bowl in the crown of the piston face, okay, or we can use both combination of these. Now, up till now we have studied the SI engine. Now let's see the combustion in CI engine. That is a little bit different than the SI engine. Combustion in compression ignition engine is quite different from that in an SI engine, whereas combustion in an SI engine is essentially a flame front moving through a homogeneous mixture. So in SI engine, it is essentially a flame front moving through a homogeneous mixture. Combustion in a CI engine is an unsteady process occurring simultaneously at many spots in a very non-homogeneous mixture at a rate controlled by fuel injection. So in CI engines, the combustion is an unsteady process occurring simultaneously at many spots in a very non-homogeneous mixture at a rate controlled by fuel injection. Because the incoming air is not throttled, pressure in the intake manifold is consistently at a value close to 1 atmosphere, with engine torque and power output controlled by the amount of fuel injected per cycle. So everything depends upon the controlled amount of fuel which is injected by the fuel injector. This makes the pump work loop of the engine cycle very small. The lower loop, the B segment in your PV diagram. This makes the pump work loop of an engine cycle very small, with the corresponding better thermal efficiency compared to an SI engine. This is especially true at low speed and low loads when an SI engine would be at part throttle with large pump work. So therefore the CI engine, the work net is equal to work gross minus work pump, and the work pump is very small. So work net is equal to work gross in CI engine. Now, events what are happening before the injection of the fuel. Let's see. Only air is contained in the cylinder during the compression stroke. So no air fuel mixture in CI engines, only the air is contained in the cylinder and that is compressed in the compression stroke. Late at the end of the compression stroke, we inject fuel. So the compression ratio of the modern CI engine ranges from 12 to 24. Compared to normal SI engines, high thermal efficiency fuel conversion efficiencies are obtained when these compression ratios are used in equation, which we have studied in chapter 3. The thermal efficiency of Otto cycle is 1 minus 1 over RC, that is compression ratio. K is, specific gas, specific heat constant, K minus 1. Now, thermal efficiency of a diesel is equal to 1 minus bracket 1 over RC raised to K minus 1. Beta is the cutoff ratio. Beta raised to K minus 1 divided by K beta minus 1 bracket close. And for thermal efficiency of a dual cycle is 1 minus 1 over RC K minus 1 bracket. Alpha is pressure ratio. Beta is your cutoff volume ratio. K minus 1 divided by K alpha beta minus 1 plus alpha minus 1. However, because the overall air fuel ratio on which CI engines operate is quite lean, so the equivalence air fuel ratio is phi is equal to 0.8. Less brake power output is often obtained for a given engine displacement. So most of the CI engines, as we have studied, operates in a lean region, and the equivalence ratio is 0.8 at which they operate. So due to which we have a less brake power output is often obtained for a given engine displacement. Fuel is injected into the cylinder late in the compression stroke, as we know that in CI engine by one or more injector located in each cylinder combustion chamber. So at the end of the compression stroke, when your piston is about to reach TDC, we inject the fuel in the combustion chamber. Now, injection time is usually about 20 degree of crankshaft rotation. So the injection time by the injector of fuel is 20 degree of crankshaft rotation, starting at about 15 degree before TDC and ending about 5 degree after TDC. So when your piston is at 165 degree before TDC, right, you are taking 0 from bottom dead center and 180 at top dead center. So the piston will be at 165 degree and will end at 185 degree. Okay. Ignition delay is fairly constant. Ignition delay is there in a real time. So at higher engine speed, fuel injection must be started slightly earlier in the cycle. So ignition delay is a property of the fuel, which is there and fairly constant in real time. So to cater for this, at higher engine speed, fuel injection must be started slightly earlier in the cycle. In addition to the swirl and turbulence of the air, high injection velocity is needed to spread the fuel throughout the cylinder and cause it to mix with the air. Now, consider your piston is moving from BDC to TDC in compression stroke. Lot of compression is there. So pressure is high, temperature is high. No, there is a swirl motion, there is a turbulence there in the combustion chamber. So you need to have an injector with a high velocity of which is more than the swirl and turbulence velocity to which if you use a high injection velocity, then it will spread the fuel throughout the cylinder and cause it to mix with the air. If the high injection velocity is not there, the fuel will be only scattered around the tip of the nozzle, so it will not spread throughout the combustion chamber. So injector must have a high injection speed velocity to inject the fuel. Now, again, you have studied this is the self-ignition temperature. If you are having this is with respect to time, so this is the ignition delay. Below the self-ignition temperature, more is the ignition delay. As you move above from the self-ignition temperature, the shorter is the ignition delay and quicker is the combustion. Now, this is the pattern of from the nozzle injector. On your top, this is your nozzle and this is the tip of the nozzle. Okay. So this is the spray pattern, which is ideal when we are injecting the fuel. So this is the theta angle, this is the spray angle, and this is the breakup length, this critical length. Droplet size of the distribution are vary. Here there will be different size, here it will be a different size. And the spray tip penetration is of this much length or this much distance. It should be covered with having that much of a pressure. So spraying angle is important, the breakup length is important, the spray tip penetration or the depth of the spray is important. Now, this is the ideal spray pattern. Now let's take an example of this heavy engine in which we have a 4 nozzles spraying. Let's suppose if we have this cylinder and we have these 4 nozzles, if they are spraying, everyone is now fuel. If all is spraying fuel in the center, so here we will not have that uniformity. It will be a completely heterogeneous mixture. The fuel concentration will be more here. Okay, so their fuel should be less. So let's see this figure here. Here, every nozzle is injecting at 90 degree to each other. So 90 degree this one 90 degree this one, 90 degree this one. With this, we are is achieving better atomization and better mixing. So the tip of the nozzle is should be placed such like that it should cover the complete cylinder surface area. Okay. Now, these were the events before the injections. Okay. 20 degree is the crankshaft rotation, 15 degree before TDC and 5 degree after TDC. Now, what happening after the injection? If we have sprayed the fuel, now what is happening inside? Now, after injection, the fuel must go through a series of events to assure proper combustion process. And what are those processes? First is the atomization. The fuel breaks into very small droplets. So from large molecule size to smaller molecule size. The smaller the original drop size emitted by the injector, the quicker and more efficient will be this atomization process. Basically, atomization is the mixing process of the fuel with the air. Now, if we are using the injector with a very small diameter of at the tip, so it will emit smaller size of the molecule droplets of the fuel, and those will be quicker and more efficiently atomized with the air. Now, second is the when you have a smaller size, they will evaporate quickly. Vaporization. The smaller droplets of a liquid fuel evaporates to vapor quickly. This occurs very quickly due to the hot air temperature created by the high compression of a CI engine. As we have studied, the compression ratio at which they are operating is 12 to 24. So high compression ratio means temperature is high, pressure is high. So this occurs will very quickly due to the hot air temperatures created by the high compression of a CI engine. Now mixing. After vaporization, the fuel vapor must mix with the air to form a mixture within the air-fuel range, which is combustile. So after atomization, vaporization, the mixing is the process. After vaporization, the fuel vapor must mix with the air to form a mixture within the air-fuel range, which is a combustile. Now, this mixing comes about because of the high fuel injection velocity added to the swirl and turbulence in the cylinder. So, the high fuel injection velocity is the factor which is causing, along with swirl and turbulence, the mixing in a better way. Then self-ignition. At about 8 degree before TDC or 6 to 8 degree after the start of the injection, the air-fuel mixture starts to self-ignite. So, as in case of SI engine, the spark is detected after 6 degree of crankshaft rotation. So, if it is the injection is 15 degree before TDC, so at about 8 degree before TDC means 7 degrees has passed. So 8 degree before TDC after the start of the injection, if it is 15 degree before TDC, the air fuel mixture starts to self-ignites. Actual combustion is preceded by a secondary reactions, including breaking down of large hydrocarbon molecules into smaller pieces and some oxidation. These reactions caused by the high temperature air and exothermic and further raises the air temperature in the immediate local vicinity. This finally leads to an actual sustained combustion process. So at about 8 degree before TDC or 6 to 8 degree after the start of the injection, 7 degree after the start of the injection, the air fuel mixture starts to self-ignite because we have studied that the injection time is 20 degree of crankshaft rotation and it starts 15 degree before TDC. So somewhere at 6 to 8 degree after the start of the injection, the air fuel mixture starts to self-ignite. Actual combustion is preceded by secondary reaction, included breakdown of large hydrocarbon molecules into smaller species and some oxidation. These reactions caused by the high temperature air and exothermic and further raises the air temperature in the immediate local vicinity. This finally leads to an actual sustained combustion process. Now, let's see this figure first. We read this. Fuel jet of a CI engine showing air fuel vapor zone around the inner liquid core. The liquid core is surrounded by successive zones of vapors, which are A. This is your injector, which is injecting this fuel, and this center portion is the liquid core. It is surrounded by successive vapor zones of vapors, which are A. This A zone, which is around the liquid core, is too rich to burn. Too rich to burn. We have more quantity of fuel in this region. Okay. Then B is rich combustible. This B region after the A is rich combustible. C is the stoichiometric region, means the desired amount of air and fuels or air fuel ratio is in the C region. D, lean combustible region. We have a less amount of fuel and more amount of air here in the D region. And E, too lean to burn, means maximum amount of air in E region. Okay, but it is compressed with high temperature and high pressure. Self-ignition starts mainly in zone B. Zone B is your rich combustible area. Solid carbon soot is generated mostly in zone A and B. A is too rich to burn and B is rich combustible. So in this region, B is the region in which we get the self-ignition in B zone B, and solid carbon soot is generated mostly in zone A and B due to large amount of hydrocarbon present with respect to the air. Okay. Now combustion. If first was the atomization, then vaporization, then mixing, then self-ignition. Now as atomization, vaporization, mixing, self-ignition, now combustion. Combustion starts from self-ignition, zone B, simultaneously at many locations. So it may be here, it may be here, it may be here, it may be here, or it may be here, or it's in B region or in B zone, anywhere. So combustion starts from self-ignition simultaneously at many locations in the slightly rich zone of the fuel jet, where the equivalence ratio is phi is equal to 1 to 1.5, zone B. At this time, somewhere between 70 to 95% of the fuel in the combustion chamber is in vapor state. So when combustion starts, multiple flame fronts spreading from the many self-ignition sites quickly consume all the gas mixture, which is in a correct combustible air fuel ratio, even where self-ignition would not occur. So this B region, we have a self-ignition here, and this will quickly consume at this time somewhere between 70% to 95% of the fuel is combustible chamber is in vapor state. When combustion starts, multiple flame fronts spreading from the many self-ignition sites quickly consume all the gas mixture, which is in correct combustible air fuel ratio, even where self-ignition wouldn't occur. This gives a very quick rise in temperature and pressure within the cylinder shown in figure this one. The higher temperature and pressure reduces the vaporization time. So we have a high temperature and pressure in the combustion chamber. So it reduces your vaporization time and the ignition delay time for additional fuel particle. So and plus reducing the vaporization time and the ignition delay time for additional fuel particle and causes more self-ignition points to further increase the combustion process. Let's see. Now, figure 7-16, cylinder pressure as a function of crank angle for CI engine. Point this on your x-axis we have a crank angle and on your y-axis we have a cylinder pressure. Point A is where fuel injection starts. So it is 15 degree before TDC, standard we take. So this is your compression stroke. Piston is moving from BDC to TDC and compressing the air fuel mixture. We have generating a high compressive heating. So temperature is high, pressure is high. 15 degree before TDC at point A, your fuel injectors start injecting. A to B is the ignition delay. A to B is the ignition delay. So this is 8 degree as we have studied. And at point C, here your ignition starts. And at point C is the end of the fuel injection. So at point C, this is 5 degree after TDC. So the total is 15 plus 5, 20 degree of the crankshaft rotation. So point C is the end of the fuel injection. If the cetane number of the fuel is too low, the greater amount of fuel will be injected during ignition delay time. So it depends upon the cetane number also. When combustion then starts, the additional fuel will cause the pressure at point B to increase too fast, resulting in a rough engine cycle. So this will happen like this. Now, liquid fuel is still being injected into the cylinder after the first fuel is already burning. Means your burning starts at point B after the ignition delay, but you are still injecting the fuel till point C. So liquid fuel is still being injected into the cylinder after the first fuel is already burning. After the initial start of the combustion, when all the air fuel mixture that is in a combustible state is quickly consumed, the rest of the combustion process is controlled by the rate at which fuel can be injected, atomized, vaporized, and mixed into the proper air fuel. This rate of combustion, now controlled by the injection rate, can be seen in figure 16 in the slower pressure rise that occurs after the initial fast rise. Combustion lasts for about 40 to 50 degree of the engine rotation, much longer than 20 degree of fuel injection. So up till at point C, fuel injection stops. But this is at 5 degree after TDC. But the combustion till 40 to 50 degree after this point will remain there. So combustion lasts for about 40 to 50 degree of engine rotation, much longer than the 20 degree of fuel injection. This is because some fuel particles takes a long time to mix into the combustible mixture with the air, and the combustion therefore lasts well into the power stroke. Now, type of injections. We have two types of injection, direct injection and indirect injection. Now, first is the direct injection. In direct injection, engine have large open chambers without the need for high swirl. They generally have very high injection pressure, which gives the fuel jets high velocity. This assures that the penetration of the jet reaches across the large combustion chamber and greatly assists in the mixing of the fuel and air. Direct injection engine generally have a higher brake thermal efficiency because they operate slower, which reduces friction losses, and they have lower combustion chamber surface area to volume ratio, which reduces heat losses. So if we have a direct injection, engine have large open chambers without the need for high swirl. They generally have a high injection pressure, which gives the fuel jets high velocity. This ensures that the penetration of the jet reaches across the large combustion chamber and greatly assists in the mixing of the fuel and the air. Direct injection engine generally have higher brake thermal efficiency because they operate slower, which reduces friction losses, and they have lower combustion chamber surface area to volume ratios, which reduces heat losses. Now in indirect injection, the second type of injection system, we have indirect injection. Engines with divided chambers injects the fuel into a smaller secondary chamber and can use much lower injection pressure. So the injection in the secondary chamber where we do not require a high injection pressure, we require a much lower injection pressure. This gives lower fuel jet velocity, which are adequate to penetrate across the smaller combustion chamber because the secondary chamber space or the volume is very small or less. So we require a very low fuel jet velocities, which are adequate to penetrate across the small combustion chambers. The higher fuel generated in the secondary chamber provides the needed mixing of the fuel and air. As the gas mixture in the secondary chamber combusts, it expands through the orifice into the main chamber, carrying liquid fuel droplets with it and providing swirl in the main chamber. Here, the main portion of the combustion occurs much like an SI engine. The higher speed at which indirect injection engines generally operates make them better automobile engine. The higher speeds at which the indirect injection engine generally operates make them better automobile engine because of large surface area to volume ratio in the combustion chambers, and there is a greater heat losses, and this typical requires a high compression ratio. Now the fuel injection. Let's talk about something nozzles, fuel injectors. The nozzle diameter of a typical fuel injector is 0.2 to 1 millimeter. The nozzle diameter of a typical fuel injector is 0.2 to 1 millimeter. An injector may have one nozzles or several, so it depends how much nozzles have in this injector. Velocity of the liquid fuel leaving a nozzle is usually about 100 to 200 meters per second. Very, very high. Okay. So the velocity of the liquid fuel leaving a nozzle is usually about 100 to 200 meters per second. This is quickly reduced by viscous drag. This velocity of the injecting fuel is quickly reduced by viscous drag, evaporation, and combustion chamber swirl. The vapor jet extends past the liquid jet and ideally just reaches the far walls of the combustion chamber. Ideally, it is like this. But the evaporation occurs on the side of the fuel jets while the center remains liquid. So center is normally in liquid form. The evaporation is on the outer in the zone E. Liquid drop diameter size leaving the injector is on the order of 10 raised to power minus 5 meter or 10 raised to power minus 2 millimeter and smaller, generally with some normal distributions of size. So very, very small size. Factors that affect droplet size includes pressure differential across the nozzle. So factor that affects droplet size includes pressure differential across the nozzles, nozzle size and geometry, fuel properties and air temperature and turbulence. Higher nozzle pressure differentials gives smaller droplets. So we have a higher pressure differential across the nozzles, which gives us smaller droplets. Ignition delay and cetane number. Once the air-fuel mixture is in combustible air-fuel ratio and the temperature is hot enough for self-ignition, ignition delay will still be in the range of 0.4 to 3 milliseconds. So it will be of 0.0004 to 0.003 seconds. Ignition delay will be there. An increase in temperature, pressure, engine speed, and or compression ratio will decrease the ignition delay time. So if we increase the temperature, pressure, engine speed, or the compression ratio, it will decrease the ignition delay time. Fuel droplet size, injection velocity, injection rate, and physical characteristics of the fuel seems to have little or no effect on ignition delay time. So although there will be some effect, but that in comparison to temperature, pressure, and engine speed and compression ratio, this will be very minor. So fuel droplets size, injection velocity, injection rate, and physical characteristics of the fuel seems to have little or no effect on the ignition delay time. At higher engine speeds, turbulence is increased, wall temperature is higher, and ignition delay is decreased in real time. However, ignition delay is almost constant in cycle time, which results in a fairly constant crankshaft angle position for the combustion process at all speed. So ignition time is for a definite time period. Okay, remember this thing. Normal cetane numbers of commonly used fuel are in the range of 40 to 60, as we know from your chapter 4. The normal cetane number ranges from 40 to 60. In this range, the ignition delay time is inversely proportional to cetane number. So ignition delay is inversely proportional to cetane number. Cetane number and octane number are also have a strong inverse correlation for most fuels. Cetane number is inversely proportional to octane number. Cetane number can be changed by blending small amount of certain additives to the fuel. Additives that accelerate ignition includes nitrites, nitrates, organic peroxides, and some sulfur compounds. So in octane, to increase the octane number, we use tetraethyl lead, but to increase the cetane number, blending of small amount of certain additives to the fuel that additives accelerate ignition includes nitrites, nitrates, organic peroxides, and some sulfur compounds. Soot. Soot is basically the solid particles which we obtain in the exhaust. Let's see the soot. The flame in the CI engine is highly non-uniform because we have different zones and ignition is happening at different places. So it is highly non-uniform. When self-ignition occurs, the flame will quickly engulf all parts of the combustion chamber that have an air-fuel mixture in a combustible ratio at that region. Mixtures with an equivalence ratio in the range of 0.8 to 1.5 will support combustion. Some of the reaction will be in a lean mixture, some will be at or close to the stoichiometric, and some will be in a rich mixture. So it's a heterogeneous mixture. In the combustion zone, where the mixture is rich, there is not enough oxygen to form stoichiometric carbon dioxide. Instead, some carbon monoxide and some solid carbon will be formed in the reaction product. So hydrocarbon plus oxygen plus nitrogen, we get in product, we get some moles of carbon dioxide, carbon monoxide, some solid carbon particles, vapors of water plus nitrogen. So these solid carbon particles are the black smoke seen in the exhaust of the large truck and railroad locomotives. So these solid carbon particles are the black smokes seen in the exhaust of the large trucks and railroads locomotive. CI engines operates overall lean and they have a high combustion efficiency, which is generally around 98%. Of the 2% of the combustion in efficiency, about half appear as hydrocarbon emission in the exhaust. Some hydrocarbon components are absorbed on the carbon particles and carried out in the exhaust. If 0.5% of the carbon in the fuel were exhausted as solid particles, the resulting smoke would be unacceptable. This means that the amount of solid carbon being exhausted must be kept well below 0.5%. Because of the 98% fuel conversion efficiency and their high compression ratios, the thermal efficiency of the CI engine is high compared to the Otto cycle SI engine. However, because of their fuel lean operation, their power output per unit displacement volume is not good. Now, talking about this emission, the carbon emission in state of California, after every certain time period, your vehicle has to be examined for your smoke testing. So if your smoke tested is not in this range, the desired range, your vehicle registration is not extended. So you need to repair or have a good uh, mechanic to solve this problem. So now the last topic of this combustion is the cold weather problem. Starting a cold CI engine can be very difficult. The air and fuels are cold. Engine is cold, air is cold, fuel is cold. So fuel evaporation is very slow and ignition delay time is lengthened. So fuel is evaporating very slowly. So when fuel is evaporating very slowly, the ignition delay time will be more. Lubrication oil is also cold, its viscosity is high, and distribution is limited. So the starter motor has to turn the cold engine that is poorly lubricated with high viscosity oil. This results in a slower than normal turnover speed to start the engine. So more load on your self-starter and batteries. This results in a slower than normal turnover speed to start the engine. Because of the very low engine speed, the greater amount of blow-by past the piston occurs, reducing the effective compression. So because of this low turnover speed to start the engine, a greater amount of blow-by past the piston occurs, reducing the effective compression. As the starter motors turn the engine to start it, air within the cylinder must compress enough to raise the temperature well above self-ignition temperature. This does not readily happen. The slower than normal rotation of the engine combined with the cold metal cylinder walls promote a large heat losses to the walls and keep the air temperature below that needed to self-ignite the fuel. So problems. To overcome this problem, a glow plug is used when starting most of the CI engine. Remember, this glow plug is different than your spark plug. Glow plug is used in CI engine and spark plug is used in SI engine, and there is a difference between the glow plug and the spark plug. A glow plug is a simple resistance heater connected to a battery with the heated surface located within the combustion chamber of the engine. So for a short time period, 10 to 15 seconds before starting the engine, the glow plug is turned on and the resistor become red hot. So in a diesel vehicle or in CI vehicle, before starting, we switch on the glow plug for 10 to 15 seconds. So basically it's a simple electric resistance. We are giving current to this resistance. The air in the vicinity of that resistance start heated up. Now, when the engine is started, combustion in the first few cycles is not ignited by compressive heating, but by surface ignition of the glow plug. So, due to heating of this small resistance, the engine is started. Combustion in the first few cycles is not ignited by compressive heating, but by the surface ignition of the glow plug. After just a few cycles, the cylinder walls and the lubricants are warmed enough, so more normal operation of the engine is possible. The glow plug is turned off and self-ignition caused by the compressive heating occurs. So basically, glow plug is an ease to start the cold engine or CI engine. Another cold weather problem encountered with the cold CI engine in trucks and automobile is pumping the fuel from the fuel tanks to the engine. So another problem. Often the fuel tank is located some distance from the engine, as we have studied in trunk or in rear, and the fuel supply lines runs outside the warm engine compartment. The high viscosity of the cold fuel oil makes it very difficult to pump it through the long, often small diameter fuel lines. Some diesel fuel will even gel in the fuel tanks in the cold weather. Many vehicles overcome this problem with an electric fuel tank heater and or by recirculating the fuel through the warm engine compartment. So either we place an electric fuel tank heater in the fuel tanks, which heat up the fuel, or by circulating the fuel pipelines through the warm engine compartment. As much as twice the needed fuel is pumped to the engine compartment. The excess fuel, after being warmed in the engine compartment, is recirculated back to the fuel tanks, where it mixes with and warms the rest of the fuel. It is often necessary to change to a higher grade fuel oil for winter operation. So in winter, we need to change the fuel and oil with respect to the temperature changes. So higher grade fuel oil for winter operation is used in automobile in winter. More costly higher grade fuel has lower viscosity and is more easily pumped. The higher grade fuel is costly. It has a lower viscosity, so it is easy to pump. It also works better through the fuel injectors. So with this, we comes to the end of the chapter 7. I hope you have understood something. So kindly like and subscribe my video.